Hey everybody, sorry for having to cancel class today. Thank you for tuning into this video. This will replace the lecture that we would have had in class if we met today. So I'll jump right in. The topic for today is hypothesis tests for a single population proportion. We're expanding on what we did last time. Last time, if you remember, we did hypothesis testing for a single population mean. Um, Luckily, we don't need to really learn anything new here. We're just shifting from a mean as our population parameter to a proportion as our population parameter. So we're measuring group sizes, percentages. And luckily, also, like the tools we need are a little bit easier to use. So with proportions, we'll generally be able to use the normal distribution. If you remember from last time with means, we had to use the t-distributions. So we had to worry about degrees of freedom and those sorts of things. What I'm going to do is I'm going to roll through the slides as kind of usual. Then we'll hit some examples. I'll do kind of a split screen when we hit the examples. I'll show the example text on one side of my screen. Then I'll share a OneNote page that I can write on top of on the other side of the screen where we'll do out the problem. And I'll show you how to work in Excel to calculate the values that we need to calculate along the way. So let's, if I can figure out how to start this, start the slide deck. So again, we're talking about hypothesis test for a single population proportion. What we're really trying to do here is investigate whether a population proportion, remember that's group size, is greater than, less than, or has changed from some previously accepted, assumed, or required value. So a reminder on proportions. Proportions are associated with categorical variables. They measure the relative size of a group within a population. So maybe a group accounts for 60% of a population or 12% of a population. Those proportions take values between 0 and 1. A proportion being equal to 0 means none of the items in the population have the characteristic that we're interested in. A proportion of 1 means every item in the population has that characteristic. And proportions in between measure, again, the relative size of the subgroup in our population that has the characteristic we're interested in. We can also calculate proportions for sample data. So if I collect data from n individuals, maybe 100 individuals to make things easy, and I observe some number of individuals within that sample having the characteristic I'm interested in, maybe it's having red hair. So I have 100 individuals, 13 of them have red hair, then the proportion within my population, my sample, is 13%, 13 divided by 100. And so again, we can calculate that sample proportion. Our goal, though, is to talk about or to make claims or test claims about the entire population proportion. And we'll need to use sample data in order to do that. Again, there's a little bit of good news for us here. We don't need to learn anything new here. So we have the general strategy for conducting hypothesis tests. So there's a document there that gives you kind of a step-by-step for how to run through the procedure for conducting a hypothesis test. It is kind of a lengthy procedure, but there's there's good news for us as usual, and it's that regardless of what type of hypothesis test we're trying to run, the procedure is the same. It follows the same general framework. So we'll start by reading the scenario. We'll state the hypotheses for the test. We'll always have a null hypothesis and an alternative hypothesis. I'll ask you to draw a picture of the samples that would lead you to believe the alternative hypothesis instead of the null hypothesis. That will help us at the end of the procedure when we're calculating probability. We'll set the level of significance. That level of significance is our threshold for what it means to be unlikely. We're essentially measuring how likely is it that our sample data was generated from a reality in which our null hypothesis is true. If our sample data was unlikely to be observed, we'll go back and we'll say the null hypothesis was unlikely to be true, we'll reject it and we'll accept the alternative hypothesis. If our sample data was not unlikely to be observed in a reality where the null hypothesis is true, well, then maybe the null hypothesis really is true. We'll fail to reject it. Be careful, we will never accept a null hypothesis using the statistical tools and procedures that we're working with here in MAT240. In order to get to the point where we can assess whether our sample data is unlikely or likely, we need to obtain a probability associated with observing our sample data. It's a two-step process to get to that probability. First, we need to take our sample data and convert it into a test statistic. That test statistic is a boundary value on the distribution that we're using to model the sampling distribution. Remember, this is the distribution of sample statistics, whether that's sample means or sample proportions. So today we'll be focusing on sample proportions. Once we have that test statistic, that boundary value, we can convert it into a probability. We'll call that probability a p-value by using the appropriate probability function in Excel. So the functions that we've seen so far are norm.dist for calculating probability underneath a normal curve, and t.dist to calculate probability associated with a t-distribution. Luckily, in the case of proportions, we won't need to use the t-distribution. We'll be able to use the normal distribution as long as our success-failure criteria are satisfied, which, remember, says that we need to have a large enough sample so that we expect to see at least 10 successful outcomes and at least 10 failed outcomes. Once we have that p-value, that probability from the normal distribution, we'll compare the p-value to our level of significance. Remember, that's our threshold for what it means to be unlikely versus not unlikely. If the probability of observing our sample data is less than that threshold, so that probability is low, we'll reject the null hypothesis and accept the alternative. Essentially, we're saying it's unlikely that our sample data was generated from a reality in which the null hypothesis holds. If our p-value is at least alpha, then we're saying that our observed sample data was not unlikely in a reality where the null hypothesis holds, and we fail to reject it. Again, we do not accept the null hypothesis. And then finally, we'll interpret the results of our hypothesis test in the context of the scenario. The other thing that we'll make use of here today in our examples is the standard error decision tree. Remember, this is a document that allows us to find in that test statistic formula how to calculate this denominator, the bottom of that fraction, the standard error. The standard error is going to change from one application to the next, and this tree helps us find out how to calculate the standard error. So these ending boxes have standard error formulas in them. So we're about to hit the examples. In those examples, we're going to be asked to conduct hypothesis tests. The majority of these examples investigate a population proportion. I'm going to stick just to those examples. When we encounter an example that deals with a population mean, I'll skip over it for this video, but we'll identify how we know that it involves a population mean and not a proportion. We will use that general strategy for conducting hypothesis tests. We just won't flip back and forth to it. But you'll notice if you have your sheet out while you're watching this video that we are going through the steps from that framework. Slowly but surely, as you do more problems, as you work through more hypothesis testing scenarios, you'll need that strategy sheet less and less. But for now, feel free to continue leaning on it. All right, so I'm going to do split screen now. Let's see if I can get this slide to show on the left-hand side of the screen only. Make it reasonably large. And we'll find the first example that we were working on. Okay, so here it is, smartphone ownership. I'm going to make this a little bit larger so that hopefully you can read it on the video. The scenario here says that a 2015 study on technology adoption in a city claimed that 85% of adults own a smartphone. In a recent random survey of 507 adults, 466 reported owning a smartphone. Conduct a test to determine whether the proportion of smartphone ownership now differs from 85%. So I'm going to add a page to my OneNote notebook here, and I'm just going to label this smartphone ownership to keep our work kind of organized. Ownership. And we'll start. So I'm going to draw on the screen here. Hopefully it's legible. We are running a hypothesis test. The reason we're doing that is here in the text of the problem. Sorry for that pop-up. We are conducting a test to determine something. So sometimes your scenario will come out and say that you want to conduct a test. Other times you will see the word evidence. So the scenario will ask whether the sample data provides evidence to suggest something. In both of those cases, a hypothesis test is almost surely what we're working with. What are we conducting a hypothesis test on? It's this technology adoption, and really it's the proportion of adults who own a smartphone. And so if we think about the participants in this study, they're these 507 adults. The question that they're being asked is, do you own a smartphone? And the responses to get back from that question are either yes or no. And so this is a grouping question. It's a binary grouping question. And because that question sorts individuals in our sample into groups, we're dealing with proportions here. In order to start the problem, after reading it, our next step is to write down our hypotheses. As usual, we will have two of them. So I'm going to write hypotheses here. Please excuse my handwriting. And again, we'll have two of them. We're going to have a null hypothesis, and we'll have an alternative hypothesis. Because we're working with grouping data, we're working with proportions, we know that the symbol that we use is going to be the P symbol, not the mu symbol. And also we've got everybody here belongs to just one group. All of these 507 adults belong to just one big group. They're part of one big population. Later on in our course, we'll talk about how we might be able to investigate subgroups of a population. But for now, one group all the time. So at this point, we know that the parameter that we're using is a proportion. It'll be P. And we've said that always in the null hypothesis, we're going to use an equal sign. As soon as the parameter that we've used in the null hypothesis is a P, we know that that same symbol is going to be used in the alternative hypothesis, so we get that for free. What we want to do in our null hypothesis is assume that there's nothing to see here. Everything is as it was, nothing has changed. And so what we'll assume is that the current state of smartphone ownership matches the state of smartphone ownership from 2015. If there was no change, there really is nothing to see here. And so in 2015, there were 85% of adults owning a smartphone. So our null hypothesis is going to be is 85%. Once we've written that down, we also get for free that the proportion involved in the alternative hypothesis is going to be the same number. All we've got to decide is what goes in between these. I'm going to see if I can erase those arrows. It won't let me do that. I think I have an eraser here somewhere. Maybe not. in any case, we've got our hypotheses written down, except for the symbol that appears between the proportion and the 85% in the alternative hypothesis. In order to determine what goes here, remember it's going to be one of three symbols. It'll be either a not equal to symbol if we're just looking for a change or for a difference. It'll be a greater than symbol if we're looking for an increase, or it'll be a less than symbol if we're looking for a decrease. Here, we're trying to conduct a test to determine whether the proportion of smartphone ownership now differs from 85%. So differs from 85% could mean two things. One, the new proportion could be below 85%, or the proportion could be above 85%. And for that reason, we'll use a not equal to symbol here. And so now we've got our hypotheses. There they are. We're going to start by assuming, let's see if I can change colors here briefly. We're going to start by assuming the null hypothesis is true. So we're assuming that the current state of affairs is 85% of adults own smartphones for all of the work that we're about to do. Okay, so I'm going to get back that black pen. I'm going to scroll a little bit here just so we have some more room. The next thing we're going to do is we're going to draw a picture of the samples. Let me see if I can type this instead of writing it. So a picture of the samples leading us to believe the alternative hypothesis HA instead of the null hypothesis HO. And so here is our sampling distribution. It will look similar to a bell curve. So I did my best there. We are assuming, again, that the population proportion is 85%. 85% of adults own smartphones. So we'll put that in the center of our sampling distribution. If you remember, the central limit theorem said for proportions, the distribution of sample proportions will tend to look like the normal distribution, which is centered at the population proportion, here 85%, and it has a standard deviation or a standard error that we can calculate. And we'll see how to calculate it later on. So here's our sampling distribution. What we're saying by drawing this is that we know when we go out and collect sample data, we're going to be able to calculate a sample proportion of adults who own smartphones. That sample proportion, though, is unlikely to be exactly 85%. It is likely, though, to be near 85%. And so if we're looking for the samples that would lead us to believe the alternative hypothesis instead of the null hypothesis, well, those would be sample proportions that deviate far away from the 85% that we're assuming. So if we get a very, very low sample proportion, so one of these guys down here, I don't know why it stopped writing. There we go, we're back. Or if I get a very, very high sample proportion, one of these samples up here, then these are unlikely samples, and they'd lead us to question whether 85 actually is the number in the center of this distribution, or if that number in the center is something different. And that's really what we're trying to figure out here. So we have a picture of those samples that would lead us to believe the alternative hypothesis instead of the null hypothesis. We'll come back to that towards the end of the problem because this picture will help us calculate the probability of observing a sample like ours. Here, the next thing we want to do is set our level of significance. Our level of significance is what it means to be unlikely. So level of significance. And the symbol that we've been using for that is alpha. That's a standard symbol. And here we're not told to use a particular level of significance. What I've said for our class is that if we don't see a level of significance, we'll use 85%. Sorry, we'll use 5%, not 85%. So we'll set alpha here to 5%, like 0.05. What this means is that if our sample data appears with less than 5% likelihood, we're going to reject the null hypothesis and accept the alternative instead, claiming that our data was generated from a population whose population proportion of adults owning smartphones is not equal to 85%. It is something different. Okay. At this point, the work begins. We're going to start by, so we need to somehow calculate a probability associated with observing our sample data. We're going to start that process by calculating a test statistic. So test statistic is equal to, here we have a point estimate. So a point estimate. We're going to subtract away a null value. So subtract away a null value, and we're going to divide that by a standard error. So we need to find these three quantities before we can calculate our test statistic. I'm going to type a little bit more because my handwriting on the screen is not excellent. So the point estimate always comes from your sample data. So the point estimate comes from sample data. It is a sample estimate of our population parameter. Here, that would mean, so that would be a sample proportion of adults owning smartphones. And in the problem at hand, I think we have enough information to calculate that. We have some information about a recent sample we took. In that recent sample, there were 507 adults, so that's our sample size, and 446 of them owned a smartphone. So we can identify now that sample proportion. We can call it P hat if we want, or just P, whatever your preference is going to be 446 over 507. I'm going to head over to Excel and grab an estimate for that. So bear with me as I pull up Excel. Here, we'll pull up a blank workbook. Wait for it to load, maybe. Here we go, a blank workbook. And then I am going to try to increase the size here, if I can, of the cells so that it's easier to read for all of us. Okay, so I'm going to leave this kind of in the middle of my screen. So right now, we have a sample size, which is 507. We have a point estimate. That's going to be equal to, remember, we can type equals in an Excel cell, indicating that we want Excel to calculate something. 446 divided by 507. There is our point estimate. And we'll come back here in a little bit to calculate our standard error. For right now, we're going to pop back to the scenario and to our OneNote page before coming back to Excel pretty quickly. So the next thing we need is a null value. So the null value comes from our null hypothesis. That's the one that we've labeled H0 or HO. It is the assumed value of the population parameter. And so if we go back to our hypotheses, we see here's the null value, here's the null hypothesis. We've assumed there that the population proportion of adults owning smartphones is 85%. And so we're going to come back down here and identify that our null value is 85%. So null value 0.85. I'm going to get the point estimate here. Our point estimate was 0.8797, let's say. So I'm going to come back. Oops. 0.8797 was our point estimate. And now we have the two out of the three pieces for our test statistic. We've got the entire top of that fraction, the point estimate. Again, that's our sample statistic, minus our null value. The null value is the assumed value of the population parameter. What we've just done, if we subtract these now, is we found out how far away our point estimate was from the expected assumed population parameter. We need to standardize that by using the standard error. The standard error is what's going to change from one application to the next. So the formula here changes, but we find it using the standard error decision tree. So we'll pop over to that decision tree, we'll identify our standard error formula, and then come back here. So here is our tree. I'm going to make it a little bit bigger. We're not going to be able to see the whole thing all at once, but we'll start at this top bucket. We're running a hypothesis test, and we want to know whether our hypotheses involve the mean, mu, or the proportion, p. Here we have said we're dealing with a proportion, so we're going to move down and to the left on our tree. And now we want to think about how many samples have we taken? How many groups are we comparing to one another? Be a little bit careful here. This is not the sample size. This is how many groups we have, how many times we went out and collected data. Here, if we go back to the slide, we're just interested in adults. So adults are one big population in this city. And so we're not comparing two groups against one another. We've just got one group that we're working with. And so in that case, we land in this box with standard error equal to the square root of the proportion times 1 minus the proportion over the sample size. You'll notice that this box does not have any information about degrees of freedom in it. Degrees of freedom, if you remember, was DF, and that indicated that we had extra uncertainty associated with our sampling distribution. We got kicked out to a T distribution instead of the normal distribution. Here, there is no information about degrees of freedom. We have less uncertainty here, and so we're okay using the normal distribution. And so coming back to our OneNote screen, we have now the formula for our standard error. It is SE is equal to this big square root P times 1 minus P over N, the sample size. Now, the P that we're using in this standard error calculation is our best guess at the correct population proportion. We have two proportions floating around here. We have the assumed population proportion, that 85%, and we have the one that we've estimated using our sample data. Our best guess at the true population proportion, because we're assuming the 85% here is right, is the 85%. So when we're doing these hypothesis tests with a single population, with a single proportion, we're going to use that null proportion in our calculation of the standard error. And so here, we've got that this will be equal to, let's see if I can get my pen back, equal to the square root of 85%, so 0.85 times 1 minus 0.85, all divided by our sample size. And our sample size here was 507 individuals. We'll head on over to Excel to calculate that. As a reminder, you can hard code your numbers. So here, our null value is 85%. So you can hard code these numbers to calculate your standard error, or you can use cell referencing. I'll show you both ways. So I'll start with hard-coded numbers. So this is SQRT for square root, 0.85 times 1 minus 0.85 divided by 507. You'll notice that Excel here is color matching on the parentheses. So I have red parentheses around 1 minus 0.85, and I should get a black parenthesis here to close out my square root. So the black closing parenthesis matches the black opening parenthesis, indicating which parentheses are paired together. So if I calculate that with those hard-coded values, again, just typing in the numbers, I get my standard error. If you prefer to use cell referencing, you can do that. So we've got square root. Here, the assumed proportion that we're using is in cell B3. We're going to multiply that by 1 minus the value in cell B3, and we're going to divide by our sample size, which was in cell B1. If we run this, we're just referencing the values in those cells. They're the same values as we typed in by hand. We get the same quantity back. So our standard error now is 0.01586 or 0.0159. And so we'll drop that in here. So 0.0159. And so now we have all three pieces for our test statistic. We've got the point estimate, which was, again, our sample proportion of adults owning smartphones, the 87.97%. We have our null value, which was the 85%. We got that from our null hypothesis. It was our assumed correct value. And we have our standard error here, which we've just calculated at 0.0159. And so now we're ready, finally, to compute the test statistic. So compute the test statistic. And so we'll use the formula that we had written down earlier. I'm not going to rewrite it just because I don't want this video to be extra long, just to write things down. So here's the formula. We're evaluating the point estimate, which will be 0.8797 minus our null value. That's the 0.85 divided by our standard error, which is the 0.0159. So here our test statistic is approximately equal to our point estimate. Again, 0.8797. So 0.8797 minus our null value, 0.85, all divided by our standard error, which was 0.0159. 0.0159. And we'll head over to Excel and get an approximate value for that. So test statistic here. And again, you can hard code or use cell referencing. I'm going to use cell referencing. So this is equal to B2 minus B3. So that's our point estimate minus our assumed null value. Make sure that you're wrapping these up in parentheses. You want this quantity to be the top of a fraction. And we're going to divide that by our standard error, which is in cell B4. And we get 1.87. So 1.87 here. We've calculated our test statistic. That's great. Now we're most of the way to finding our p-value. If you remember again, the p-value is the probability that we would have observed a sample like ours. So observing our sample data under the assumption that the null hypothesis is true. That test statistic that we just calculated is a boundary value. So now we're calculate the p-value. And in order to do that, we're going to draw a picture again. We're going to compare this picture to the picture that we drew earlier. So here's our normal distribution. Again, we can use the normal distribution here because when we used that standard error decision tree, we did not land in a box that had degrees of freedom in it. The normal distribution is a reasonable model for the sampling distribution here. Once we use the test statistic formula, the distribution that we're working in has changed. This distribution now has a mean of 0, and it has a standard deviation of 1. Always when you use the test statistic formula and you end up with a normal distribution, this is the case you're in. So mean is 0 and standard deviation is 1. That test statistic that we found is a boundary value associated with our sample data. So I'm going to put that boundary value here, 1.87. There's the boundary value. And we're generally interested in samples like ours or even more extreme than ours. And so the samples that are more extreme than ours, oops, I've lost my pen again. The samples that are more extreme than ours are out here into the tail. We know from our earlier discussions on probability how to calculate that tail area. We're interested in the area to the right of our boundary value. That norm.dist function that we use to calculate probabilities gives us the area to the left by default. And so we are going to take 1 minus norm.dist. The 1 minus will give us the area to the right of that boundary value, 1.87, 1.87, mean of 0, standard deviation of 1, and then always with these dist functions, we're going to use true as that last argument. So we'll never use false for those. So true. TRUE, all caps. All right. And if we calculate that in Excel, we will end up getting this area there. So I'm going to head to Excel and I'm going to do that. So we'll use equals 1 minus norm dot dist 1.87 with a mean of 0 and a standard deviation of 1, and then true always as that last argument. And we get that that area is about 3%, 0.0307. So we'll track that back down here. So this is about 0.0307. At this point, we're going to check back in on our original picture that we drew. So the picture of samples leading us to believe the alternative hypothesis instead of the null hypothesis. And we're going to notice that there's not just one area there that we were interested in. We were interested in 2 areas. If this is the scenario that you're in, all you have to do to compensate for that is to double the area you found. We were looking for 2 areas. We only found 1. Let's multiply by 2 in order to get both areas. So our p-value then, p-value here is going to be 2 times that 0.0307. So I'm going to come back here to our Excel sheet. I'm going to calculate the p-value. This is going to be 2 times the value we just calculated, which was in cell B6, and got to remember to hit the equal sign there. So 2 times the value in B6, we get about 6.15%. So coming back to our OneNote notebook, the p-value again is about 0.0615. So we've calculated our p-value. We've done all of the hard work now. The last bit is to interpret the results. So here we're going to compare our p-value to the level of significance. That level of significance is alpha, which is also the threshold for our sample being considered unlikely. Really, what we mean there is samples, our sample and samples even more extreme than ours. So our p-value is about 6%. If you remember alpha that we set earlier in this problem was 5%. So our probability that we calculated is more than alpha. So our p-value is greater than alpha. Our sample data is not unlikely. So I'm going to type this again. Our sample data is not unlikely, even in a reality where the proportion of adults owning smartphones in this city is still 85%. And so because our sample data wasn't unlikely, we'll fail to reject the null hypothesis. So the null hypothesis, again, that's the one that we labeled HO. It may be the case that smartphone ownership for adults in the city is still 85%. So we're not saying that it is the case that the smartphone ownership is 85% still. We're saying it is perhaps that case. It is plausible that 85% is still the value. All right, that was a pretty lengthy example. What I'd like to do maybe is one more with you all before this video gets too long. Generally, I talk kind of slow. You can watch this on 1.5 or 2 times speed maybe, but still, I don't want you sitting in front of your computer just watching me for hours on end. So we'll add another page here. We'll take a look at another example that might be interesting to us. So a couple of other examples. We have one on candidate support. We have one on data analyst salaries. We have one on emissions tests, hospital stay lengths, online shopping and impulse purchases. We've got lots and lots of examples here that we can revisit later on. I think the question I want to do is this emissions testing one. I want to point out, though, that some of the questions we scrolled past are not examples of scenarios that involve hypothesis tests on proportions. In particular, here's one, this data analyst salaries example. In this one, you're collecting data from data analysts and you're asking them what their average salary is, or what their salary is, sorry. Numbers that can come back from that may be, I earn $55,000 a year. I earn $64,000 a year. Those are numeric quantities, and we'd summarize those numeric quantities by using averages. So this is an example of a hypothesis testing scenario where you're working with means. You'd revert back to what we had talked about last time. All right, so let's see if we can run through this emissions test example. So emissions test. We'll do this one a little bit more quickly. So historically, 95.6% of vehicles in Springfield pass the annual emissions test. The state EPA is investigating whether Quick Fix Auto, the auto repair shop, famous for their tagline, "If you got money, we got you, no questions asked." Certainly a very reputable shop. We're wondering whether this shop is passing vehicles at a higher than expected rate. We looked at a random sample of 335 vehicles that were tested at Quick Fix, and 329 of those passed. We want to know, does this sample provide significant evidence that the proportion of vehicles passing the emissions test is higher than the expected value here at Quick Fix Auto? All right. So we are running a test. We know that because we're wondering whether this sample provides significant evidence, and evidence is the key word there, that the proportion of vehicles here passing their emissions inspections is higher than the expected value. So we're not trying to estimate a proportion here. We are trying to test a claim. We're trying to investigate the value of one. Since we're running a hypothesis test, again, we're going to start with hypotheses. So hypotheses, we will always, again, have two of them. We'll have a null hypothesis labeled HO. Here, we're going to assume that there's nothing to see. Everything is on the up and up. That population proportion P is equal to 95.6% at Quick Fix Auto. Since we're doing math with these decimal values, we'll take the decimal form. So instead of writing 95.6%, we'll write that the population proportion of vehicles passing inspection is 0.956. The alternative hypothesis that we're investigating now is that perhaps Quick Fix Auto is passing vehicles at a higher rate than what we would expect. So we're wondering whether the proportion there is higher. That's an increase. And so the symbol that we're going to use in the middle here, so remember we get the P for free, we get the 0.956 for free. It's just what goes in the middle that we need to figure out. But here, that's a greater than symbol. Again, because we're wondering whether the proportion passing is higher than the expected value. So we have those hypotheses. Next thing we're going to do again is we're going to draw a picture of the samples. So samples leading us to believe the alternative hypothesis, that's HA, rather than the null hypothesis, that's HO. So again, drawing a picture here, we've got a bell curve. We're assuming that the true population proportion is 95.6%. So we're assuming that null hypothesis. That would mean that in the middle of this sampling distribution is a proportion of 0.956. Again, we know when we go out and collect sample data, we'll get values hopefully around 0.956 because that's the center of this distribution. Samples that would lead us to believe the alternative hypothesis instead of the null hypothesis would be samples that have an unusually high passing percentage. So they'd be up here in the upper tail. There's only one way that samples could lead us to believe the alternative hypothesis instead of the null hypothesis here. It would be higher than expected proportions. Lower than expected proportions wouldn't satisfy this alternative. Okay, so again, we'll come back to that towards the end of this process. We're going to set our level of significance. So level of significance here is going to be 5% again because we're not told to use anything else. So alpha equals 0.05. And when we do that, we're saying that the samples that would lead us to believe that alternative hypothesis account for 5% of samples total. So we're wondering whether our observed data is one of these 5% rare, unusual samples that would lead us to believe the alternative hypothesis instead of the null hypothesis. At this point, we've got to calculate the probability of observing a sample like ours. In order to do that, we need to calculate a test statistic on our way to calculating a p-value. Again, the formula for that test statistic is always the same. I'm going to draw this out. So again, it's our point estimate. So point estimate minus our null value divided by our standard error. Again, the point estimate comes from our sample data. So in the problem, we collected data from QuickFix. They had a random sample of 355 vehicles. That's the total sample size. 329 of those passed. And so the proportion that we're going to calculate here is 329 out of 355. So I'm going to get us a new sheet. I'm going to make the cells a little bit bigger here. Oops, I'm hitting the wrong plus sign. So our point estimate is, I think it was 329 out of 335. Let's check back and make sure that that's right. So yeah, out of 335 cars, 329 passed. So that gives us our point estimate. While we're here in Excel, we can give our null value. Our null value was 0.956, I think. Yeah, 95.6%. And so we can drop those into our test statistic formula here. We've got 0.9821 minus 0.956. And then we've got to identify our standard error. And so we'll go to the decision tree in order to do that. So our standard error calculation here is going to be, if we pull up our tree, again, we're running a hypothesis test. We're doing a hypothesis test involving a proportion. So we're on the left-hand side of the tree. All of the cars here belong to the population at QuickFix Auto. So we've got one sample. We're in the same boxes we were in last time. And so our standard error formula is going to be SE equals the square root of the proportion times 1 minus that proportion divided by the sample size. Now remember, the proportion that we're going to use here is our best guess at the true correct population proportion. Because we assume the null hypothesis is true, is correct, that's the proportion that we're going to use in our calculation of the standard error. So I'm going to draw out that calculation. We'll go to Excel to run it. So here we've got a square root 0.956 times 1 minus 0.956. Oops. We'll head back there. All divided by our sample size, which was 335 cars here. So we'll run to Excel and we'll compute that. So standard error. So we have equals square root now we're going to take our null value, that's the assumed correct value, B2, times 1 minus B2. We're going to divide that by our sample size, 335. And we get 0.0112. So we'll come back to OneNote and we'll drop that in. So our standard error is approximately 0.0112. And now, again, we've got all of the pieces that we need to calculate our test statistic. That test statistic again. So test stat is equal to our point estimate, which was 0.9821 minus 0.956, the null value, divided now by the standard error that we found, 0.0112. And again, we'll go to Excel to calculate that test statistic. So test statistic here. So we've got, again, in parentheses, we want to make sure that the 0.9821 minus 0.956 is in the top of this fraction. So we're going to take the value in B1, we're going to subtract the value in B2, and we're going to divide by the standard error, which is stored in B3 right now. And we get a test statistic, about 2.33. Okay. So we're almost done, and we'll close out this video. So we've got a test statistic of about 2.33. Now we've got to convert that test statistic into a p-value. Remember that p-value is the probability of observing a sample at least as extreme as ours, at least as favorable to the alternative hypothesis. So we're, again, going to try to mimic that picture that we drew earlier on. The picture that we draw now, though, is going to no longer be centered at 95.6%. Once we use that test statistic formula, our distribution is centered at 0, and it's going to have a standard deviation of 1. So we'll draw out that distribution. Here it is. Centered at 0, standard deviation equal to 1. Here is our test statistic somewhere out to the right at 2.33. And that picture that we drew earlier had the right tail shaded, so we're going to also shade our right tail. And so we need to calculate the area to the right of that boundary value of 2.33. In order to do that, we're going to use the norm dist function, but we're going to use 1 minus it again. So 1 minus norm dot dist of 2.33, our boundary value. Our mean is 0 in this distribution. Our standard deviation is 1, and then all caps true will get us our approximate probability. So 1 minus norm dot dist 2.33 with a mean of 0, standard deviation of 1, and true. And again, I forgot to hit the equal sign at the front of this cell. So there we are. So we get 0.0099. So our area here in this tail is approximately 0.0099. And that's that area there. If we scroll back up to the picture that we drew originally, that picture only had a single tail shaded in. It was only that upper tail. So we do not need to multiply by 2 here. The value that we found is our p-value in this case. So we only needed to find one area. We found that one area. All right. So our p-value is approximately 0.0099. We're going to compare that p-value to alpha. So compare the p-value to the level of significance. That's alpha. Our p-value here is 0.0099. Our alpha value was 5%. So our p-value is less than alpha. So p-value, my pen doesn't want to write anymore, it's tired. P-value is less than alpha, which means that our sample data is unlikely to appear under the assumption of the null hypothesis. So we observed something unexpected. In this case, where our observed sample data and samples more extreme than that are unlikely, we're going to reject the null hypothesis. So reject the null hypothesis, that's HO, and accept the alternative to it, that's HA. What that means for us is that quick fix auto is passing vehicles for inspection at a higher than expected rate. So their pass rate is above the average of 95.6%. All right, I think I'm going to close it out here. This has been over an hour. I hope you find these example problems helpful. We'll do more examples when we meet in class next time. Thanks, everybody.